So thank you very much. Thank you for the invitation. So this tutorial will be on computational social choice. And as opposed to essentially all the talks you've heard so far, I would say all the talks you've heard so far were from producers of parameterized complexity. But I am a consumer of parameterized complexity. We actually we need the results that are being created here to solve our own problems. So if you ever wondered if there's someone who cares about your results, it's me. and of course, all the other people from the community, and of course, a couple of other communities. And computational social choice is actually a very large field of research. It's computational social choice, otherwise you can call it, it's about collective decision making. So it's about voting, it's about judgment aggregation, so things like if people come to court and some judges actually, or have to make a decision if there was a crime or not, somehow you have to aggregate their knowledge, and this is what judgment aggregation, for example, is studying. It's about fair allocation. So if you share a taxi ride, how do you share the costs? Someone gets off earlier, someone gets off later. How do you, divide your rent? How do you split your possessions when you divorce? That's all studied there. It's part of computational social choice. Matching with preferences as well. So problems such as if students apply to high schools have preferences over students as well because they want good students. Somehow you have to make the matching. That's part of the research as well. And in addition, a large chunk of cooperative game theory is in fact studied within computational social choice. However, all of that, I will focus on voting. And one of the reasons for that is, that's my field of expertise, but also that's where traditionally computational social choice started. So if you're interested in this area, of course, the tutorial cannot cover everything. So here we're already limiting ourselves. There's a book, Handbook of Computational Social Choice. The PDF is available on the internet for free. I think on the legal website it's password protected, but the password protected is available on the internet as well. And and it's not because it's not against the publisher. The publisher somehow agreed that we can spread it around. So if someone wants it, then it's for sure available.
Seems to trivialize many of the allocation problems.
It certainly helps, and so you can see that there's a reason for the word social in our name. The handbook is from 2016. There's also a recent book from 2017 about recent trends, and there's also a bunch of surveys. And the reason why I'm focusing also on voting is that I checked, it has 19 chapters, of which 10 are on voting. So if we're doing approximation, we're doing very well. Of course, you could also say if it's parameterized complexity, I should just spend more time and talk about everything, but fine. Okay, so if we're focusing on voting, one of the things that, I'm not sure if I'm allowed to say such things, but as opposed to theoretical research, computational social choice comes from both theory and AI and from applied people, and essentially it's not okay to just study problems. You also have to explain why you study them. So the reason why voting is important is, of course, first of all, we have politics. We have presidential elections, parliamentary elections, deciding laws, policies. There are all sorts of properties there that you may want to care about that are non-trivial. Voting happens a lot, and this is actually much more of a focus on, or this is essentially equally important focus of computational social choice, is that in the business settings, there's a lot of decisions to be made, and as opposed to politics, in business applications, it's very easy to change voting rules, because just some people agree. So for example, Wikimedia Foundation uses advanced voting rules, whereas all your presidential elections are run by 1, 2, 3 different voting rules throughout the whole world. So many business applications are actually important. Another important application is in multi-agent systems. And I would say some years ago it was a dream that we will be using voting to solve many problems for multi-agent systems, but in fact it's slowly becoming a reality. So now, since it's 2017, I can already say things such as in the beginning of the 21st century, there was actually an application, a meta search engine, that was based on a nice voting rule, Kameni's voting rule, that was aggregating data from a bunch of search engines, and it was competitive with Google at the time. So it was able to produce as good results simply by making search engines vote on what's the answer for a given query by using a good voting rule. There are applications such as, for example, genetic algorithms. In a genetic algorithm, you often have this selection procedure that selects some individuals that have to keep on in the new epoch. And we can actually use advanced voting systems to improve these algorithms, to give them some properties that they don't have otherwise. Okay, so in other words, whenever we aggregate opinions, social choice and voting happens. Okay, so we're focusing on computational social choice and on what I call single winner voting. So you can think of it in terms of presidential elections. So that's the easiest metaphor to keep in mind, that you want to elect a single guy. And of course, in spite of the fact that there will be lots of pictures in this talk, this is actually serious mathematics. So we need some formalism. There are basically two approaches. One of them is that we can take an approval model where people specify who they say is an okay president. And it's a very nice model, but in the single winner setting, it's not. I mean, it's interesting, but there are many other things in the ordinal model on which I will focus on, in which we rank people, or we rank candidates. So formally, the setting is as follows. Imagine that an election is a mathematical object, just like a graph where you have a set of vertices and edges. You have a set of candidates, the red guy, orange, pink, blue, and green, and you have a set of voters, V1 through V6 in this case. And also, every voter is endowed with a preference order or with some sort of way to express preferences. And in the ordinal model, this means linear orders or permutations or whatever you call such a thing. So here, for example, voter V1 thinks that red would be the best president, then orange, then pink, then blue, then green, and so on. And one of the problems with this approach is that there is no way to specify intensities. So, for example, if V1 thought that red is the great president, but everyone else is completely rubbish, he would have no way of expressing that. And similarly, in the other way around, and well, that's too bad, but that's the standard model used in the setting. Now, when we have an election that's not enough to make a decision, we also need a voting rule, and that's essentially an algorithm or a procedure that decides who's winner. And this voting rule returns a set of tied candidates. Of course, in real life, you somehow you need to have some tie breaking. Most of the time, the set is a singleton, but due to possible symmetries in the votes, it's unavoidable that occasionally there will be a tie, and there's no fair way of breaking that tie. So in the worst case, usually systems used in practice have randomization in the end. We usually abstract away from it by simply looking at the set of tied guys, and that's it. And of course, we need to use some voting rules, so we need a procedure. So this is part of our basic setting to find the result. You can, of course, wonder who should be a winner of this voting rule, but we don't have the time to run through this exercise, so I will simply show you some rules. And the most basic family of rules that people study are called scoring rules, which essentially associate a score with every position. So in the plurality rule, you get 1 point if you're ranked first. So if someone loves you, you get a point from that person. So in this case, it's quite easy to see that red and pink are both ranked twice, whereas blue and orange are ranked first once. So the tight set of winners are these guys. So plurality is a controversial rule because it's essentially everyone in the area of social choice believes this is more or less the worst rule we can use. Okay, this is not the worst rules, we can make worse. But among those that are actually used, this is probably the worst, which means it's used in practice a lot. So why cannot we give a better rule? Of course we can, but we can't agree which one. But still, the next very popular rule is Borda, which simply means that the scores decrease linearly. So here you can see that, for example, the green lady is ranked second 5 times, so 3 times 5 is 15. She has 15 points. The red guy has also here 8 points, plus 10, 12, 14, 15. They both tied as winners. Another popular rule is K-approval. Sometimes it's as controversial as plurality, but it's a bit better. So in K-approval, essentially, if you approve of top K positions, these guys get points. And finally, okay, I told you that plurality is the worst, but actually, perhaps this one is the worst. It's veto. It's called also anti-plurality. And you're only giving 0 points if you hate someone, and you give 1 to everyone else. So it's probably not a very good rule to use in practice. But we study it a lot because it has interesting features. It's a good counterexample. So it's nice to see, usually when you get a problem, you evaluate it on plurality, you evaluate it on veto, evaluate it on borda, see what happens. And if plurality and veto give the same result, it's, oh yeah, of course it's the same because they're similar. And if it differs, it's, oh my God, it's different. And a lot of fun happens. Okay, but that's one set of rules. Another example is based on the notion of a Condorcet winner. And this leads to graphs, so that should already be exciting. So here we form a graph where every candidate is a vertex. And, for example, we form an edge from the green lady to the red guy because the green lady, in 4 votes, she is better than the red guy. So she beats the red guy 4-2. So we put an edge like this. In fact, the green lady beats everyone in this way. So we call such a candidate a Condorcet winner. And there's a belief, I mean, Condorcet, he was 18th century guy. He said that if there is a Condorcet winner, he should win, or she should win. And interestingly enough, Borda was actually a French, so Condorcet was French, Borda was French as well. They lived in the same time. And there's a proof that Borda winner, essentially, there can be a Condorcet winner and a Borda winner simultaneously, different ones. So these guys actually didn't like each other very much. So Condorcet is an, you can, yes?
Just explain it again. So if most of the times the person is better than the other one,
Yes.
then the edge goes this way.
Yes.
What if it's equal?
So if it's equal, like here, the pink lady and the orange, so pink, so orange, pink, pink, orange, pink, orange, orange, pink, tied, orange, pink, pink, orange, tied. So either you don't draw the arrow or you draw it both ways. But still, so essentially Condorcet said if there is a Condorcet winner, this should be it's a good person to win. If there is no Condorcet winner, then there are voting rules that essentially select someone who is closest to being a Condorcet winner, depending on what notion of closest. So one example I will show you is Copeland rule. And Copeland rule simply gives you 1 point for every edge that comes out. So essentially, your score is your out degree plus half of the tied score. So in this case, the green lady gets 4, the red guy gets 3 because he gets 3 points out, and the orange guy, he's losing 3 matches, but he's tied with 1, so he gets half a point. There's plenty of other Condorcet consistent voting rules like that. For example, there's a rule of Dodgson, of Kemeny, there's Minimax, whole world of them. And essentially, I would say the world of social choice is divided more or less into 2 groups. People who believe Condorcet is the right choice and you can only live if you choose a Condorcet winner or Condorcet consistent rule, or people who accept scoring rules and or maybe something else. And of course, occasionally you change this point of view in your lifetime depending on your paper, but still these are kind of 2 families of rules that are studied a lot. But there are also things such as STV, single transferable vote, which again looks weird because it's used in practice. And this rule works as follows. It says eliminate whoever has lowest plurality score until someone has majority support. This is, for example, used in Australia. So in this case, we would eliminate the green lady because she, many people like her, but no one likes her a lot. So she's out. Now, red guy has 2 points, pink lady has 2 points, blue has 1, orange has 1. Either blue or orange has to go. We break ties. Somehow, the orange goes. Now, the red guy has 3 votes, but here we have 2 and 1, so the blue guy has to go. And now the red guy has majority support, and he's elected. It's a horrible system from many points of view, but it works. It's a horrible system because there are actually cases, and you can prove it mathematically, that if you shift someone forward in a preference order, then he was winning before, but now, when you increase his support, he loses. And there are examples of things like that happening in Australia in real-life elections. The system is non-monotone, but it's actually an amazingly good system. We run some experiments trying to see how it works. It's really difficult to get better results than this thing. So I don't know how these 18th or 19th or early 20th century people come up with that, but they did. Okay, here the red guy wins. Okay, now you may wonder, is it even realistic to assume we have all these rankings? And does it really matter all that much which system to use? And this is actually a controversy that keeps happening in social choice community. Can you assume that we have these preference orders? So here's one example where you really can. This is season 2008 of Formula One racing. You can say that every race is a voter. So for example, Australia racing thinks that Lewis Hamilton was ranked first, Nick Heidfeld was ranked second, and Nico Rosberg was third. It's very unfair to the Polish player or driver, but so it goes. And if you treat Formula One racing as an election, they use a voting system which for the first position gets 10 points, then 8, then 6, then 5, then 4. Or actually, this is what they were using in 2008. Now it's 25 points for the first place, and it decreases also somehow non-linearly. But, so official ranking from 2008 is for these drivers like this: very bad, Polish good. But actually, if you used Borda scores, it's a very good system. If you use plurality, not so much. However, Felipe Massa would have complained. If you use approval-based systems, well, Felipe Massa still thinks it's a very good system. If you use Copeland, you still get a vote from Felipe Massa. If you use Maximin, which I didn't show you, but which is Condorcet consistent, Felipe Massa not so happy. But it's a great system. So as you can see, STV also, Felipe Massa is very good. So if you look at it, it was really, in some sense, a completely arbitrary decision that Lewis Hamilton won that was a world champion then. There's majority of voting systems, among those I chose to show you, is actually saying that Felipe Massa was better. So it really matters what system you choose. Yes?
Just to make sure, so this table shows how to determine the overall winner from the ranking in the different
Yes. Of course, you can ask yourself, can we choose one perfect system? And actually, the whole social choice theory started from a very simple answer to this question: no. Based on very simple axioms, you can show that it's impossible to provide a fair election rule that will satisfy everyone all the time. So essentially, you always have to choose a voting rule depending on the setting, and you always have to sacrifice something, and you have to think what and why. Okay, so that was a warm-up, and now we can discuss more about computational social choice, how it looks like. So we have this more ordinal model with scoring rules, with Condorcet rules, and all these things that happen there. There's also, so all of this is about single winner setting. There's also committee elections, but we will not discuss them today. There will be in the third part. Instead, we will focus on problems that people actually study when discussing social choice. So what can arise there? And the very basic problem is, of course, winner determination. You get an election and you have to decide who is the winner. This seems pretty trivial. For all the rules for the rules that you've seen so far, you could just compute the scores, decide everything easily, you get polynomial time. And that's almost always true in the single winner setting. but there actually are situations when it's not. So there are, in fact, rules for which computing the outcome is NP-hard, or NP-hard actually, in the case I want to discuss. And the first such example is a rule called odgson. So let's make a test. Who here heard about odgson? A lot, which is good. But in fact, every single person in the room heard about odgson. Because odgson is in fact Lewis Carroll, the author of Alice in Wonderland. He was a mathematician who was writing books like Alice in Wonderland under a pen name, but his serious, real work as odgson. So the odgson rule works as follows. We say that a odgson score of a candidate, candidate C, is the smallest number of swaps of adjacent candidates that ensure that C is a Condorcet winner. Okay, so if we have an election here, and okay, this is the election we used before, so we have the green lady as the Condorcet winner, which means that the odgson score of the green lady is 0. She needs no swap, she is the Condorcet winner, that's it. She would also then be a odgson winner, because her score is clearly lowest. But if there is no Condorcet winner, then we have to compute this value. Or in this case, for example, we can ask, what's the odgson score of the red guy? And the red guy, he's winning all his 3 matches against the orange, pink, and blue, but he's losing to green. However, he's losing only in, so essentially he has 2 times, he wins twice, and he loses 4 times. So if we make 2 swaps, the easiest ones, he actually becomes a Condorcet winner himself. So his odgson score is 2. Okay, and there's a lot of papers written about odgson elections, which again shows some peculiarity of the area, because odgson rule was actually not really meant as something to be used very much, and it has terrible properties. Well, at least bad properties. It's also non-monotone like STV. If you let's say if you have some result and you double the electorate, so you clone every person twice, and but they still vote the same, the result can change. It happens, but it's so mathematically appealing that this it was studied in 89. It was shown that it was NP-hard. In 97, there was a JACM paper that showed it was essentially. I believe this is the first theta 2p complete problem that was somehow found and studied. There's of course this very good paper that shows parametrization by the number of voters and hardness there. So there's a lot of work, and I'm absolutely convinced this system will probably never be used for anything truly important. But it's interesting. Okay, so we'll have a quick look at how is it possible that we have an NP hardness for such a basic problem as winner determination. So we will do a reduction from X3C. So X3C, so this is one of the most favorite, so there are 2 favorite problems in computational social choice. One is partition, the other is X3C. And a really large fraction of NP hardness proofs in the area are proved from these 2. Of course, for parameterized people, I guess the moment you see X3C, you should ask, why not set cover? And then you can wonder what can happen. And of course, here, why not set cover? The answer is, well, because these things are not so easy on parameterized front. There are some FPT and there are some W hardness results. Okay, but you form an election.
Could you just define the problem for us?
Oh, sure. I must say, I assume that when I say set cover, it's, but essentially, so you have these elements of sets, 1, 2, 3, 4, 5, 6. You have the sets, and your goal is, in this case, you have 3 times something number of elements. So here it's 3 times 2, 6. So you're supposed to choose 2 sets that all together, like the set 1, 3, 6, and the set 4, 2, 5, cover everything. So is that satisfying answer? Thank you. I thank you more. So we have a set of candidates, and we form a set of candidates which are the guys to be covered. They're clones, which will just serve some purpose, and the sets themselves, which also essentially just are there to fill in space in an important place, and the guy whose score we want to compute. And we create votes. So first we create votes that essentially model the X3C instance. So it means that for every set, so like the set S1, which is the blue one, we have a 1, 3, 4. So 1, 3, 4 are ahead of S1 and then P. Okay, so this way we simply want to encode the X3C instance somewhere. We have all the votes like that. Then we have what is called equalizing votes, which are always of the form a set element, his clone, then the guy that we're interested in, and then whatever else. And we add enough to ensure that every set element is preferred to P in the same number of votes as all the other set elements. So here, for example, 1 could belong to more sets than, well, I'm not sure if I have a good, okay, 2 belongs to 3 sets, but 1 belongs to 2 sets only, so, but we want to equalize that. So, and finally, we add defeating votes. And these votes, here I'm using some notation I haven't defined, but essentially we add enough votes where we rank all the set elements, all the clones, and then P, so that each set element I, so what this means is that there's, for each set element, so among these, we only need to make one swap. We need to push P ahead, each of them exactly once, it suffices to push P ahead each of them once to make him a Condorcet winner. And if one looks closely at this reduction, P is always preferred to all these clone guys and all the set guys. So he's defeating them in the pairwise comparisons, and he needs to pass each of these guys once. And now it's quite easy to see that P has Dodgson score 4K, which means that 4K swaps suffice to make him a Condorcet winner, if and only if there's a cover. And essentially, the reason is that if we want to cover these 3K guys that form our sets, we need to push P 4 times in each of these votes. So for each 3 element guys, we need to make 4 swaps. So there's 3K guys to pass, and we need to make 4K swaps. And we cannot do it in the equalizing voters or defeating voters, because here, to get one guy, we need to make 2 swaps. So the price for getting one guy is 2. Here, the average price for getting one guy is 4/3. And here, again, the price for getting one guy on the average is 2 or worse. Okay, so I hope that either you buy the election, or you don't care. In any case, or you ask questions. But since you don't ask questions, we will go on. So winner determination is one issue. There's actually a bunch of issues that occur around it. And these are things like, for example, possible or necessary winners. So, for example, you may have some partial knowledge about election, and you may want to predict if someone still has a chance of winning or not. One of the most interesting problems is margin of victory. This is a problem of fraud detection in elections. So you, after elections happened, you can count the votes, and you can ask yourself, is the result truly what it was supposed to, or did someone tamper with this election? And if it so happens that, for example, by changing only a small number of votes, you can ensure that someone else wins, this means that there's a high chance that this election was tampered with, so you need to try, you need to perform some sort of investigation. Of course, you don't have a guarantee, but this is a form of fraud detection that was proposed in the literature, and it's a very good application. Of course, if there's someone trying to detect fraud, that's for a reason, because we're trying to commit fraud. So the other set of results that we study in computational social choice, or the other set of problems, is about changing the result of the election. So it started with essentially with strategic voting, where, for example, someone when you go to the election booth and you are supposed to cast a vote, you can always ask yourself a question: should I vote honestly for what I believe, or should I vote for the lesser evil? But the one among the 2 guys, for example, who can win, that I can get. So if you face this problem and you choose to go with the lesser evil and not with your beliefs, it's called strategic voting. And this is one problem that was studied. It's bad, essentially, because if everyone votes strategically, all of a sudden it's possible that someone who shouldn't have won wins. Then we have problems like control, which are about modifying the structure of election. We'll see an example of that. Bribery is quite self-explanatory. And campaign management is essentially bribery, but for legal reasons. So essentially, you promise things that you will do things, and people vote for you. Okay, and there's a lot of different connections between these problems. I will not discuss too much of that. And while winner determination, except for this odgson rule and a few friends, is polynomial time, almost, not all, but almost all of these problems are NP-hard. So what do you do when you see an NP-hard problem? Parameters. Oh, complete mess. Sorry. You should study parameters, but in fact, I guess I first wanted to convince you that these problems really are NP-hard. So okay, that's a bit of a spoiler, but too bad. So let's look at constructive control by adding candidates problem. So think of presidential elections in the United States. So to not be too political, let's not think about the current president. Let's think Bush and Gore. That was a few years ago, but I hope you remember. So there was this huge debate whether Bush should have won or whether it should be Gore. And there was recounting of votes and all problems like that. But in fact, many people believe that Gore should have been the president if not for this nasty Nader guy who joined the election. So Nader was, if I remember correctly, he was the Green Party candidate who essentially had similar platform to Gore, maybe more extreme. But essentially, whoever really thought Bush should have won wouldn't vote for neither Gore nor Nader. But if you supported Gore, but you were even more radical, and Nader came up, said, okay, maybe I should follow my beliefs, and I will vote for Nader. So that steals a vote away from Gore. And some people believe this is why Gore lost. Some people believe this is nonsense. But still, at least, the debate happens there, and it's a real issue. So in the control problem by adding candidates, what we have is we have an election, but some of the guys are not really running in the election yet. So some of them are not registered. So we ask if we can make a certain candidate a winner by adding a given number of spoiler candidates. And by the way, if you think it's not a real issue, there was an example in the United States when the candidate from, if I remember correctly, Republican Party, went around and collected enough homeless people that he registered as candidates on the Democratic ballot so that people wouldn't know who's the actual real Democratic candidate. He really did it, he admitted he did it, he published a newspaper article on it. And, or at least someone wrote an article about it. Okay, so in this case, if we want to make the pink lady win, she has 2 votes, but the green lady has 3. So if we add an orange guy, he steals away 1 vote from the green lady. It's tied, so maybe we're not happy. We can still add a blue guy. Now the green lady wins. And this problem is NP-hard. And again, reduction from X3C shows that this is NP-hard. And the reduction is actually very easy, so you can very quickly get the gist of what's happening. So we have this set of guys to cover sets. So in this case, the guys to cover are the colors. We have sets like this. And we form an instance of control by adding candidates. So these will be our candidates, the colors here, and they have appropriate scores. But we will also have candidates to be added, and these are our colorful guys as well. And we build the election in such a way that our preferred guy has t plus 1 points, where t is just some number that came out from the construction. And we make sure that all these colorful guys, all the element guys have t plus 1 scores as well. And we can easily do it because it's a plurality system, so you just get 1 point for being ranked first. So it's very easy to form an election like that. However, we also, for every set, we build a vote where the set element, we build 3 votes in fact, where the guys, the element guys are ranked second, and the set guys are ranked first. However, the set guys are not registered. These are the spoiler candidates. And now clearly you see, and we make sure, of course, that these points stay like that with these added. And now this is clearly a set cover instance, because, for example, you can see here that we have all the guys. So the sets, the blue set and the pink set, they cover everything. So when we add them, when we add these spoiler guys, they still vote from each of the guys to be covered, and we have a correct reduction. So again, I hope this is clear enough. So control problem is NP hard. And so are almost all the problems there. So what do you do when you have an NP hard problems? Of course, that was my planned trick. I wanted to say parameters, and it shows that. So of course, one of the first answers from theoretical algorithmic people would be approximation. But this is actually very often not a good answer in the world of computational social choice. If you're computing election results, imagine this, you're going to win because it seems you have an approximately high score, but perhaps this guy next to you has more, but we couldn't compute. So you cannot use approximation algorithms for winner determination unless you're not in the politics world. And in fact, in my third lecture, I will give you a lot of situations where approximation is okay. And you can use approximation for campaign management, but very often it really is that you need to study parameters, because often you really need an exact solution. Or if it's a bribery problem, as someone once said, it's difficult to convince your boss that you need to pay $1 million in bribes, even though it's a 2 approximation, so maybe 500,000 would be enough. Okay, so what parameters do we study? Usually it's election size, so number of voters, number of candidates. What is called, I guess, here standard parameter, so the budget or the cost that is studied within the problem. And these are, I would say, the 3 main parameters. When you start with a problem, these are to look at. When you're a bit tired of a problem, you can look for special features. Yes?
What is the size of your instance?
So size of the instance is typically number of voters times the number of candidates. But it's typical to separate and study number of voters, number of candidates separately. I mean, because if you study them together, it's not very interesting, of course. Okay, so for winner determination and number of candidates, there's a very easy. We can show how Dodgson score becomes FPT, and this is actually this proof was probably repeated, of course, not for Dodgson, for many different problems. I would say until the last year or two, all the proofs on parameterizations by number of candidates looked the same. Essentially, what they said is, so we have this, whatever setting we have, number of candidates, we will, if the parameter is number of candidates, the answer is ILP. Always. I mean, there are some examples maybe, and the way it works is that, and people really, until recently, were quite lazy on this. And I mean, I was one of them, so I can say that. So we know that if there are m candidates, there are m factorial possible votes. So let's say Ni is the number of voters with a given preference Pi. Xij will be a variable in our ILP that says how many votes do we move from having preference order Pi to having preference order Pj. And then we will have a constant that says in the vote Pi, D is ranked higher than C, then this constant is 1, otherwise it's 0. And we have a constant we can compute easily in polynomial time, number of swaps to transform Pi into Pj. Okay, so when we have these variables, forming an ILP is extremely easy. We will minimize the Dodgson score as follows. So for each pair of vote preference orders that we change one into the other, first we cannot cheat. So we cannot somehow do negative number of swaps. Second, so for each I, so each vote is transformed into equal number of votes. So maybe xii will be some non-zero value, the guys that stay, and then all the other xij's are the transformations that are being done. Then for each candidate D, and what it says here is for each target preference order J, the number of guys that were transformed from I to J, where D is ahead of C. So essentially, here we sum up the number of votes after transformation, where D is preferred to C, where C is the guy whose score we want to compute, is smaller than the number of votes where C is preferred to D. So essentially, we make sure that C is a Condorcet winner after the transformation. And then it suffices to count the number of swaps. We ensure the odgson score is at most D, the value that we minimize. We run Lenstra, and we're happy. And this is it. Almost all these proofs look like that. Tomorrow, I will give some more references where actually recently more interesting things started happening. To see how easily you can actually improve this algorithm. So here, if we're running this algorithm, if you have m candidates, you have at least m factorial times m factorial variables. If m is 20, maybe not a huge election, 20 factorials times 20 factorials, that's a lot. Obviously, you will, if you try to run Lenstra, that will kill you. If you try to run actual ILP solver, that will kill you. But if you realize that actually there's absolutely no point of having all the m factorial times m factorial variables, because if you want to ensure that someone is a Condorcet winner, that a guy C is a Condorcet winner, the only reasonable choices are that in the votes that already exist, you push this guy forward. And then instead of m factorial times m factorial variables, you can have, let's say, n, which is the number of votes, times m variables. This is not FPT. But in fact, this n is smaller than n factorial, because, of course, if it was greater than n factorial, then you just use all these things that you had before. So you can actually, essentially, by making these slides, I was able to improve, the result that I made myself without checking the literature. But actually, the literature is filled with examples like this, where it is relatively, it should be somehow. So essentially, the whole area of computational social choice was using parameterized complexity. So far, I would say mostly in the classification manner. So we have an FPT algorithm, yes. We have a W1 hardness, but we have FPT approximation scheme, yes. And no one, I would say, okay, not no one, but until recently, very few people cared about the running times of these things, and I think it's high time to change.
Has this algorithm been observed in the
wild? It's a bit difficult to say if it was observed in the wild, since the Dodgson rule was not.
Exactly, so it's an algorithm that doesn't work for a problem that's in the
Yes. So it seems I think that explains why there were so many theoretical papers on it.
No, but you said that it's the same algorithm for all things where you have few candidates and these things happen in the wild.
Oh yeah, of course, yes. But the benefit of speaking in this audience is that, okay, in computational sociology, I have to explain why we study things. Here, I can just say we study things. Okay, so we also saw this example of control and number of control problem, which was NP hard. And here, parameterized complexity actually gives us something spectacular. And it takes a moment of thinking why it is spectacular, but it truly is. Because, okay, so this plurality control problem, which I have shown you, is W1 hard for the number of voters. It's with a relatively tricky reduction. And to witness that it's tricky, we made a mistake in it, and it was corrected by others. Actually, I would say this is the true. This is a moment of pride when I write a paper and someone actually reads it and finds a bug, because every paper has some bug. And okay, so here we have this W1 hardness, and okay, the problem was NP hard. We have W1 hardness. What's so special? However, if we move to a destructive variant of the problem, and in the destructive variant of the problem, instead of trying to make someone a winner, we want to prevent someone a winner. So the first paper that studied destructive control problems, the title was Anyone But Him. It was actually during the times of Bush-Gore election, and the title was supposed to be different, but they changed it. So it was a common belief that destructive problems are easier than constructive ones, because the goal is, instead of making someone specific win, you just make anyone else win. And there were some examples of that, but very few. And for example, for plurality, both the constructive and destructive problem is NP-hard. And parameterized complexity finally gave a tool that allowed us to make a lot of distinctions between destructive and constructive problems, where constructive is, say, W1 hard or W2 hard, but destructive is actually FPT. And that was the case here. And we're slowly running out of time, so I will go quickly. The algorithm is actually exponential time kernelization. The way it works is that if we have a despised candidate red, we guess a defeater. So we guess someone who will get higher score than the guy. So essentially, the defeater doesn't have to win the election, but he has to be better than red. So to follow it, it's when you're running away from a tiger, you don't have to be faster than tiger, you have to be faster than your friends. So we have an election, and here we have some votes which are essentially set from the point of view of red and green guy. So here, green lady is first, and she is so we add her to election if she was a spoiler candidate. So we will not change the result here. Here, the red definitely will get points. Here, some other registered candidate definitely gets points. And here, some other registered candidates is ahead of both green and red. So maybe this blue guy will lose points later, but we don't care, because we only care about giving the green lady more points than the red. And we also have the remaining part of the profile where we actually can make a difference. So the boring part we get rid of, and the interesting part, we notice that it's enough to keep essentially an exponential number of different candidates, where here n is the number of voters, and for every candidate, he has a signature. So either he's before both green and red, or he's after both green and red, or he's in between, and they're ranked in various orders. In fact, you don't need these 4 options. In fact, it suffices to keep 2 options. Either a given new guy is taking a point away from whoever was first among registered, or he is not. And this means that there's 2 to the power of n different signatures of the candidates. And if our goal is only to to ensure that the green lady has more points than the red, it only matters by adding these new guys, how many times a red guy loses a point and how many times a green lady loses a point. And for that, the signatures are enough. It's also easy to show that we can keep only n, so polynomially many registered candidates, which means we get a kernel. Okay, and this way we can solve it. We can actually, in the paper where it was done, we sort of mentioned kernels. Kernels actually have not received so much attention in the.
Just to make sure I understand the problem. After doing this, then you remove all the candidates from the ballot that you didn't need for this.
No, so I check. Essentially, yes, I remove from consideration all the spoiler guys that I didn't need. I keep only 1 for each signature, and I solve the instance somehow. So brute force gives me FPT already. Dynamic programming actually gives 2 to the power of n running time. So here it's one of the few cases where there's actual kernel and when there's reasonably good running time. Okay. So there's also some other things that one can do. So for example, there are things. So essentially, before parameterized complexity, we also, or now we still do, we look at restricted domains. And this is essentially a notion similar to, so what happens to an algorithmic person who runs into a difficult graph problem? Well, they think of trees. They find a tree, they solve a problem, there it's easy, and then when there's an easy algorithm on trees and it's hard on graphs, then of course the next thing is tree width and things like that. So we don't really have a good, tree width notion like for computational social choice. But here, since I'm essentially out of time, I will flash you with the idea that there is something called single-pickedness, and people tried to develop something like tree width. It was called single-pickedness width. It has, this is the picture. So this is, this is almost like tree width. So essentially, single-pickedness is a bit like tree for us. So what trees are to graphs, single-pickedness is to preference profiles. And this single peak in this width was trying to copy that idea. The problem is that it's an extremely fragile notion. So even a single voter, by changing his vote a little bit, can completely spoil it. So it's not a very robust notion, so it didn't catch up very much. So some three-width-like notion for us would be very nice, but we don't have it. And the summary is that it's computational social choice is a nice field, an application domain for parameterized stuff. A lot of classification results in the literature, but few kernelization results, few attempts to optimize FPT algorithms. So it's probably there's plenty of results that where you can improve the running times. The motivation matters. So when you improve running times or when you write your own papers, I would say a community is very open to new people entering the community, but you have to you somehow have to justify your studying an interesting problem. Okay, and this is it.